you're smart people, you know you're around people that probably have it. If you feel symptoms, get tested. Stay as safe as possible. I'm going to try to make this video stuff online. We'll try to work through this. It's going to be a rise at the beginning of the semester, it's predicted, and it'll fall off in paper. But again, you probably know more about it than me. I'm taking a lot of vitamin D. I'm taking probably 10,000 units or more. It's more than recommended, but I know it's safe. I'm taking a lot of stuff, but I'm staying away from gatherings. I'm trying to do smart things. You're very young. You're going to survive this probably without much problem. I'm a little older. However, the real problem is even young people, when they get it, some people have lasting effects, so try not to get it. That's the bottom line. Now, that said, back to business here. And if you feel unsafe, you don't have to be here right now. I just want you to know that. I'm trying to help everybody. And I got nothing from the university administration yet on this, so this is just me speaking. All right? So don't hold me to anything I say today. But I want to make these lectures available online. I've done it for 10 years. I've done it more than 10 years, and I think that'll help you. Has anybody looked at the video that was online besides me? You have? Who has? Raise your hand. You have? 2 people? It was a little tough to read on the far side, but he's got a new camera, so hopefully it'll work fine. Thank you again for doing it. Now, questions about the homework or about any material that we've covered so far? Anybody? You 2 have questions, class, or at least concerns? No? Anybody? This is a different class. I'm usually inundated the first student. Nothing at all. Did you all see the solutions too? Let me ask you this, how many did it? I mean, I'm not going to come down on it if you haven't. If you did it, you understand it then? Whenever I get this, it concerns me. Is there anything you didn't understand that I could clarify? Because usually one or two people that haven't understood, they don't understand something. There's more than that. They just don't know they don't understand. Anything? This is always strange to me because I'm used to being clobbered by questions. Nothing? Wow. Okay. All right, we'll continue. I'm probably going to do a problem. All right, we've gone through the wave equation. We developed the basic solution of the wave equation for any environment, right? The E field and the H field. You all with me? And I showed you the trick to get E from H and H from E, right? So, as a matter of fact, let's just do this. Suppose I had an E field that looked like this. This will be in the phasor domain. I have an E field that's 10 e to the minus j 50 x in the AZ direction. We'll assume the units would be volts per meter. This is a kind of quiz problem. And we'll assume it's in air. All right? It's a plane wave propagating. This is in the phasor domain. Y'all follow me? Now the first thing I'm going to ask, don't respond quite yet, just think about it. I want to know what beta is. That's the first thing. Just listen. Second thing I want to know is what the frequency is. Third thing I want to know what the wavelength is. Fourth thing, I want to know what the intrinsic impedance is of the medium. Fifth thing, I want to know what the H field is and how you get it. So here are 5 very basic things that if you've done the homework, you should be able to obtain and listen to the lecture very easily. First is beta. Now, who can tell me how to find beta? Anyone? Go ahead.
Just the coefficient of the J-term.
It is going to be the coefficient of the spatial variable. In this case, it's multiplied by j, so there is no alpha, it's just beta. You all agree? So beta is 50. Are you with me, everyone? Next, from that, how do we get the frequency or wavelength or any of these other terms? Which one do you want to try? Somebody else, if possible. Anybody in this room? How do I get the frequency? Or how do I get any other further information? Wavelength, anything else? This row? Anything? Now this is stuff you should know pretty much like the back of your hand. Go ahead.
You gotta use beta.
Okay, do you know how?
Lambda, C over beta.
Well, what he's saying is he knows one thing. He knows when it gets to the cosine argument, it's going to be beta z. He remembers something like that if it was in the z direction. Well, which way is it actually propagating? Maybe I should put this down. What is the direction, unit vector in the direction of propagation? Now take a look at this and make sure this is a basic quiz right here. This would be a very easy quiz. I give you 5 minutes. What direction is it propagating and how do we know? Anybody? Well, we always look at the coefficient of the exponential and we see the spatial variable. You see that x in there? That tells us it's in the x direction, but is it positive or minus? Because there's a minus j, it's in the positive x direction. Do y'all hear me on that? Everybody hear me? So that means the unit vector in the direction of propagation would be ax and it would be positive. Y'all follow me on that? How many do? All right, please make sure you understand this because this is considered trivially basic. If you don't know this, everything else is going to be formed. I'm trying to encourage you. It's like V equals IR in circuits. You have to know the basics. All right, now let's continue on. You were going for wavelength, whoever told me. Was it you? Yeah, somebody. Somebody around here, I forgot. But you were saying, well, beta z, it would be 2 pi. Weren't you getting at that? We know beta times the wavelength would be 2 pi. Correct, class? Y'all remember me going through that already, right? So, therefore, what is the wavelength? 2 pi over 50, right? It would be in meters. You're right about that. Okay, remember this is an air or free space. That's a tip off right here about stuff. So if we have that, can we get eta right here? What is eta in general? Do you remember the formula? Eta was equal to the square root of j omega mu over sigma plus j omega epsilon. Y'all remember that? All right, in free space, how does this thing digress to something very easy to solve for? I mean, how does it change? Tell me about vacuums. Does vacuum have sigma that's non-zero? It's 0, right? So if sigma goes away, what does this become? Well, the j omegas go away and I have the square root of mu over epsilon, right? If it's free space, I have the square root of mu naught over epsilon naught, right? So this would be 1. Eta would be square root, mu naught is equal to 4 pi times 10 to the minus 7th, right? And epsilon naught, we could do it as what? 1 over 36 pi times 10 to the minus 9th. Do y'all remember doing that? What does that come out to? Well, if you do the math on this, you get 120 pi ohms, or about 377 ohms, right? Do y'all remember that from last time? Sure. So we know we've got that one. I'm checking off boxes. So this is about 120 pi. All right. How about the frequency? How do we get the frequency? Now, if you don't know it right off the bat, then think about what you do know. I try to encourage people to do this. What do you know? Well, we know beta, right? But really, we know that what? The propagation constant was alpha plus j beta, correct? We know alpha is going to be 0 because it's air, sigma 0, right? There's no attenuation. Y'all with me on this? And we know technically gamma, what is gamma? It's the square root of what? J omega mu over sigma plus j omega epsilon, right? I'm showing you the way I would think about it if you didn't understand. You shouldn't understand it like that, but if you don't, this should help. Do you all agree with me there? All right, now sigma 0 for air or free space, right? So if that goes away, really I have j omega, right? So it's j omega squared, take the square root of that. I just have j omega times square root of mu over epsilon, don't I? Now hear me, what is the square root of mu over, or mu epsilon when we're in free space? I'm getting at something very fundamental. When I have the square root of mu naught epsilon naught, that should trigger something. Isn't that 1 over c, 1 over the velocity of light? How many remember that? 1 over the square root of mu naught epsilon. This is very important. This is like a fundamental truth in physics. So the velocity of light, c, is about 3 times 10 to the 8th meters per second, and it is this is exactly equal to 1 over the square root of mu naught epsilon naught. That's what it will be. How many honestly remember it now? You should, or at least have seen it, right? Remember this in physics? Your physics teacher probably was on his, I don't know, pedestal talking about this. All right, now, if that, in our case, we don't have an alpha, we have J beta equals this, right? So write this down. If you're in air or free space, then the velocity, phase velocity is c is 3 times 10 to the 8th meters per second. That's equal to 1 over the square root of mu naught epsilon naught. And also, if you're in free space, beta is equal to omega times square root of mu naught epsilon naught. Or beta is equal to omega, which is 2 pi f, divided by c. Do you see the logic here? Think about it, what I'm doing. Y'all agree with that? Everybody agree with it? The only thing I'm doing is replacing what? I'm replacing the variables. That's beta because here sigma would be 0, right? It would just be j omega times square root of mu epsilon. If we are in free space, it's mu naught epsilon naught because epsilon relative and mu relative of 1. And furthermore, that's 1 over c, right? And then omega is 2 pi f. Do y'all agree with me? Now, do you see that c times beta over 2 pi would be f? This is one way of getting it, right? It would be c beta over 2 pi. Do y'all agree with that? All right, what's that going to be? Well, c is 3 times 10 to the 8th, right? Times beta, which is 50, right? Over 2 pi. That would be the frequency. Does anybody know another way to get frequency? There's one fundamental relationship when you're in a lossless medium about wavelength and frequency. Does anybody remember?
They're inversely proportional.
That's absolutely true. But what do you know? That wavelength is velocity, in this case c, right? It's the phase velocity divided by f, isn't it? Y'all remember that? How many do? From physics, right? It's got to be that. Matter of fact, these are one of these fundamental truths. So we've got wavelength. If we want frequency, we can get it, right, by taking just c, right, over lambda, or 3 times 10 to the 8th, over lambda, which is 2 pi over 50. Which is exactly what we had over here. So that's how you get all these values. Finally, how do I get h? This is from the last lecture. I showed you a trick. Does anybody remember? How do I get h if I know e is the propagating wave? This is part of your homework.
The 1 over eta?
You're right. These are two relationships I put down, and I'm trying to underscore the importance of this stuff. This should be second nature. You won't be able to cram for this. If you don't have this down, by the time we're into more complicated stuff, you'll really be lost and you don't know where to go. So here, I gave you two relationships. I said h was equal to 1 over eta, right? Times the unit vector in the direction of propagation crossed into the E field, right? And I said that E, if I wanted E, would be equal to minus eta, unit vector in direction of propagation crossed into the H field. Do y'all remember those? That way you don't have to do the crazy curl, right? We could always take the curl of E and set it equal to minus j omega mu h to find h. But that's an irritating thing to do over and over. This is straightforward. So what is h in our case? It's equal to 1 over 120 pi, right? That's what eta is. Do you agree with that? Then we take the unit vector in the direction of propagation, which in my case is ax, bless you, and we cross it in to the E field. And I gave the E field up there as 10 times e to the minus j 50 x And it's in the AZ direction. Now please watch this. Y'all agree with that? Watch it now. Here's where people mess these things up. I looked at the last final exam I did, and it was unbelievable number of errors right here. All right, and this stuff, I mean, when I go over it, I try to emphasize the importance of knowing what a cross product means. So when I look at this, you all see how it's AX cross AZ. All right, what is X cross Z? And I do this only for your benefit. If you go in this direction of your crossing, it's plus. I do this. You probably saw it in math. If you go the other way, if it's AZ cross AY, well, in this direction, it's minus. Do y'all remember that? So we're going AX, right, cross AZ, right? Look at this. AX cross AZ, so it's minus AY. Do y'all see that, class? So this would be minus AY when I do it. And the magnitude would be 10 over 120 pi. Now the way you always get the magnitude of the H field, you always take the E field divided by eta. That's the magnitude. But the orientation has to be perpendicular to the orientation of the E field and still perpendicular to the direction of propagation, which is X, so it has to be Y. In our case, it's minus AY. Do y'all follow me on this? Give me a show of hands, how many understand that? Now, if you were a little off guard here, didn't expect this kind of questioning, just realize if you do the homework, this should be evident. You really should. And if it's not, then let me know, and I'll make sure I give you enough problems to make it evident. This is not something, this is not deep science, this is very straightforward, 1-2 type things, right? Just basics. Okay, now we move on. I'm glad I did that. Does anybody have any news about Auburn's operations? Because I didn't get any. Nothing. Okay. Well, the next thing we're going to talk about is when we're dealing with media that is not free space, lossy media. The first thing we talk about is something where we have a permittivity that is complex or lossy. So call this a lossy dielectric. Now, what do I mean by a dielectric and what do I mean by a lossy dielectric? So I've got to explain this in a way that you can appreciate. And this is real important. You see this equation we talk about curl of H is equal to sigma E, or really it's J, and then it's plus the partial D with respect to T, or J omega epsilon times E. Y'all remember that equation? Now, J here represents real current density. By that it means if you could somehow spray paint an electron in a lattice, you could watch that electron move through in the direction of current flow. It would be real current moving. Do y'all follow me? It'd literally go back into a battery. If a battery was driving a circuit, go back around and around and around. Y'all follow me? Real charge could flow. That's J. The curl of H, sometimes my professor in college used to call it the Maxwell current density. It is a current density, but it's made of two pieces. So this is really sigma E. Sigma has to do with the conductivity. It has to do with allowing real charge to move through the lattice or move through a conductor. All right, this is real charge motion. If you spray painted electrons, you could watch them move around the circuitry. This is displacement current. Right here. Now what does that mean? Well, if you imagine a lattice, and this is the way Wentworth's book discusses it, and it's a pretty good way. When I did material science in grad school, I had a lot of stuff where professors found different ways mathematically to describe this phenomenon. But in essence, it's this. If you assume you have charged balls linked together by springs in a lab, sorry, 3D labs, they're charged balls. If you put an electric field in there, the charges themselves would stretch apart, right? Technically, when you have a dielectric, you have a positive and negative charge center. When you put an electric field, the positive charge center moves in the direction of the electric field with a force of really QE, and the negative charge moves in the opposite direction where it stretches. Does this make sense to everybody? So if you had I'm not going to put the whole lattice here, but if you had something like this, plus, minus, and then you put an E field in this direction, this would have a force in this direction, this would have a force in this direction. The net effect would be that spring would be stretched. And this distance would be delta D plus D. This is D. Y'all follow me? Now, when that stretches like that, it absorbs energy. All right, so there's more energy storage in the lattice. But also when it stretches and then recoils, because this is at a constant frequency, it dissipates energy because of frictional losses. Does this make sense to everybody? Now, I can't get into at the quantum level and stuff. Actually, at the quantum level, I'd have trouble doing this. But at the microscopic level, the type of phenomena that happens, but really what happens is there's phonons. Have you ever heard the term phonons? You know photons? Photons are what? It's what makes the electric field. If you took the whole conglomerate of all the photons at a point in space-time and integrated the values, you would get the value of the electric field at this point. I'm just saying that's what photons are. Well, when you deal with thermal energy, they're phonons. They're vibrational states that go down to quantum levels. And it would become phonons, and I don't want to go there. But that's how you really create heat. It takes electrical energy, and through friction, there's a couple of things that get really kind of bizarre, but it changes the state of the energy from electrical or from potential energy into actual kinetic energy, but it would be in terms of heat. Y'all follow me? But the charges themselves, even though there's a loss, there is no real current flow. Y'all follow me? Through the lattice. If you spray painted this ball, it would just move back and forth, but it would still cause a loss. So what we do to take care of that? We say that we're going to create a complex permittivity. Write this down, this is important. The complex permittivity will be given as epsilon prime minus J epsilon double prime. And Dr. Moore was supposed to put a little hat on this, and this is just the complex permittivity. And the complex permittivity, this would be in the phasor domain. If you plug it into the curl of H, you get this. Your sigma term here will be 0. So you get 0 for the first part plus J omega, then it's epsilon complex, which is epsilon prime minus J epsilon double prime E. Y'all follow me?
That means why is sigma 0?
We're only looking at we're going to assume that sigma 0 for a complex, or for a dielectric, a lossy dielectric, and it generally is. All the losses have to do with the actual motion I described, where the charges are bound but they're vibrating and causing heat. Y'all follow me? So let's see how the loss term creates itself. See, this right here is a loss term, right? I don't know if you remember this, but that sigma E gives rise to a power loss that is sigma E squared. That's watts per meter cubed. Do you remember that from EMAG 1? Sigma E squared would be the actual heat created in watts per meter cubed. Y'all remember that or not? No? Well, y'all at least understand I squared R heating, right? Right? And I is really V, it could be V squared over R as well, but this is really the microscopic form of I squared R heating. It's really, or V squared over R. And it's sigma E squared, and it's in watts per meter cubed. But don't worry about that yet. Anyway, it's a loss term right here. Now this, we're assuming, forget sigma, take a look at this and notice one thing. when I take curl of H here, I get, well, I have J omega epsilon, epsilon prime times E, but then I have J omega times J, which is minus, times the minus is plus, then I have plus omega epsilon double prime E. Now take a look at this for 1 second. I want you to see something. This is important. We're assuming sigma 0 just because we're talking about lossy dielectric. Don't want to confuse the fact. All right, it could have a value, but for now, forget it. I'm just talking about the loss effects due to these little charge centers vibrating back and forth. They can't move through the lattice, they can only vibrate. This is how we discuss it. Now you see this term right there, that is still the displacement current, still right here. And in fact, epsilon prime is nothing more than epsilon relative times epsilon naught. So it hasn't changed its value. That's like the good old epsilon we all know. Epsilon relative, epsilon naught. But this epsilon double prime, notice how there's no J term. It's what? Omega epsilon prime, right? See it? Times E. It's the same thing as sigma, but we don't use a sigma term here because sigma is always associated with real charge moving throughout the lattice. Here, whenever we're dealing with losses, we have this epsilon double prime, and it allows us to more or less categorize things as losses due to the dielectric thermalizing energy, all right? That's it. Now you'll see more about this in a second. You with me at least? Somewhat of an appreciation why we do what we do. But this, the omega epsilon prime, is in the same exact position the sigma would be. It's multiplying just E, it would have to do with loss, okay? Now we get to something interesting, and Dr. Moore's bookie has this shown pretty well. We talk about the loss tangent. And what we do is this. On this axis, we're going to plot the real part of curl of H. Now what I'm going to do, and this is for everybody's benefit, when we talk about curl of H, in fact, we could have a sigma, and we could have omega epsilon double prime. Both are going to be just multiplying E. That's it. These things give rise to loss, but we'll also have a plus J omega epsilon prime E, and that's the displacement current. It has nothing to do with loss. Nothing at all. So on this axis, we plot the real part of that, or what we do is we plot sigma plus, really plus omega epsilon double prime times E. And then on the vertical axis, we plot epsilon prime times omega times E. This is the real current. This is the imaginary current. If we took the imaginary portion of curl of H, we'd get this. This is called the displacement current density. And this, actually it'd be a misnomer to call it the conduction current density because only one part of it's conduction current, sigma. This is actually bound charge that's just losing energy. That's all this is. But it has the same mathematical effects. Now when we plot it, we get this. This is going to be the real part, this is the imaginary part, and this is called the loss tangent. So the tangent of that gamma there is really equal to, well, if you think it's opposite, right, over adjacent. So the opposite would be sigma plus omega epsilon double prime E over just omega epsilon prime times E. The E's will cancel. But do y'all follow me on this, class? Now, if it's a little confusing, you'll see why we're doing it. And it's basically to catalog things to get a figure of merit for how good a dielectric is. I'm going to show you this now. Now, here's the real truth about this, so write this down. Almost always, we talk about lossy dielectrics and we talk about dielectrics, we assume that sigma is about 0. That's the relative truth. Then when we take a look at the tangent of that, called the loss tan, this is actually termed the loss tangent. That's really just equal to, see how if sigma 0, the omegas go away, epsilon double prime over epsilon prime. Are you with me on this, class? Now remember, epsilon prime is nothing more than epsilon relative epsilon naught. So what this really does, and by the way, does everybody know the tangent of a small angle is about that small angle? How many do? Right? Sine of x is about x, tangent of x is about x for small values of x, and then somebody, it's a legitimate question. What's small? Small to me is of the order of like tenths of a radian. Because when you do that approximation, sine x is about x, tan x is about x, you have to be in radians. Y'all follow me on that? Not degrees, radians. So the loss tan, really, you could say that that angle in radians is about equal to epsilon prime, double prime over epsilon prime. And in your book, it'll have this. And the way what this really is telling us in one word, it's saying the smaller the value of the loss tangent, the less energy is lost in the dielectric per cycle. That's what it's really saying, the heating, all right? So you want the loss tan as small as possible. And in Dr. Whitmer's book, what he does, by the way, in the summer, we were just done with maths, and now we're back. It's hard to read people. When they got maths on, I don't know if you understand it or not half the time. I wish I could read people better with masks. So if you look at this, back in his book, I'm trying to find it. He has, in one of the appendices, a whole bunch of stuff. Lost in values. He did. Well, he used to, I thought. Okay, I don't see it in this book in the back, but let me just tell you, when you do materials engineering, when you are trying to determine the value for a capacitor's dielectric, if it has to be a high energy storage device and has to last for a long time, you don't want epsilon, you don't want it lossy, so you want the loss tan as close to 0 as possible. Do y'all follow me? That's the real bottom line. Now, I want to add one more thing. Usually, if you're trying to make a capacitor and you're worried about energy storage and things like this, the main thing you're worried about is the breakdown strength of the dielectric. And for air, I think I asked you this, but do you remember what the breakdown strength of air is in volts per meter? Anybody? It's about 3 million volts per meter. It's saying that if an electric field was impressed in this room and there was no pointy metal pieces, it would take about 3 million volts per meter. That's a pretty large electric field. Now, you can get a much smaller electric field and get that value if you have any kind of a sharp point, all right? It's field emission caused by a point, and it's because the actual electric field will cut around here to solve it. It's really a solved solution of the del squared equation, but I don't want to go there now. And you'll get a much higher electric field here, even if the static or the free space electric field is much less. It'll enhance around points. When you're dealing with dielectrics, you would like a breakdown strength maybe 100 times as much. And you would like epsilon relative about maybe 4 times better or more. It will allow you to store much more energy than you could with just an air-filled capacitor. Do y'all follow me on that, class? And that's real important. Then there are exotic materials that they make supercapacitors out of. Anybody ever heard of supercapacitors? Who has? I have a friend named Tom Birch, Dr. Birch, some of you know him. He was playing around with some of these. He got a supercapacitor and put a penny across one end and melted it.
Wow.
Now, how many guys know about starting cars on cold days? Anybody? You know that the cranking power of the battery becomes very important, right? How many amps it can put out. A battery has an enormous amount of energy stored, but they can't get it out real fast if the internal resistance goes up. And in cold weather it does. There's a long story on this. But they can take a supercapacitor and allow it to charge. And then when you turn the crank on your car, that will become the voltage. It'll be the primary current driver for a short time and get it going. Y'all follow me on that? So that's, I don't know if any new cars have this, but I know that's what they're working towards. And it'll give you this enormous amount of current for a very short time because it's storing a ton of energy. All right, and these supercapacitors have values of epsilon relative, and I'm going to say this, I'm not absolutely certain if this is correct, around 40 to 50,000. How they get it, I don't know. All right, so that's complex dielectrics. We'll see more about why this is so important later. But just realize the complex dielectric and the lossy dielectric, the loss has nothing to do with real charge moving. It has to do with things moving back and forth. And the worst type of capacitors that have the most heating from this, but they store a lot of energy, are called electrolytic capacitors. Have you all heard of those? What do you know about an electrolytic capacitor? Anyway, there's one cardinal sin if you use one that you're going to regret violating. Anybody?
They're polarized.
If you try to drive current in the wrong direction, they're polarized, plus minus. That means the dielectric orients itself, plus minus, to always have a plus to minus potential. If you try to get a negative to plus potential or drive current through it in the wrong direction, it'll blow up because then all those molecules try to flip and it causes an enormous amount of heat and kaboom. And I've seen these. I've seen this stuff blowing up. Anybody ever blow one up? You blew one up? Where? Where?
In my garage.
For kicks?
Not on purpose.
In high school,
For on purpose or accidental?
on accident.
Well, we did it on purpose when I was in the electronics shop. We used to, yeah, let's see how bad this is. Man, they're loud. My God, that's scary loud. So, and then I watched the high energy cap, the aftermath. I wasn't there when it blew up. It's literally worse than a grenade. It would have killed everybody in the room. It blew up. And this is a high energy storage capacity. And somehow they didn't have controls to prevent polarities from changing real fast. I think we're driving a railgun, but I'm not sure. Anyway, I saw the whole thing's blown out like this, shrapnel all over the place. I was so thankful I wasn't there when they did it. Anyway, that's some interesting stuff. So now we're going to go to the good conductors. I'm telling you stories. Hopefully this is of some interest. Now we're going to go to good conductors. All right. So what's a good conductor? What's a lossy dielectric? Here's the cardinal rule. When you take a look at the value of curl of H, it's equal to sigma E plus J omega epsilon E, right? That's just it, correct, class? Now, if you look at this, this is really just sigma plus J omega epsilon times E. I'm not even going to put the complex dielectric in there. I'm going to make it simple. Sigma is the real current. J omega epsilon has to do with the displacement current density. So whenever sigma is much greater than omega epsilon, we call this a good conductor. That's it. Sigma is much greater than omega epsilon. It's a lossy dielectric whenever omega epsilon is much greater than sigma. So then a logical question is, well, what happens if sigma is about the same as omega epsilon? That's a crummy dielectric. It's more than lossy, it's crummy, it's rotten, right? But at that middle ground, what I'm about to show you doesn't work. So I'm about to show you some tricks. And this is going to be for the good conductor right here. Does that make sense to everybody? Because if you look at this, sigma and omega epsilon are multiplying the value of E. If this dominates, then it's a good conductor. If this dominates, it's a lossy capacitor. Follow me, or a lossy dielectric. That's all there is to this. So now, if we assume we have a good conductor, we assume that, so sigma is much greater than omega epsilon. Then, when we look at some values, it becomes interesting what happens. First, the propagation constant is alpha plus j beta. Please watch this. This is very important that you see this part. So start, or however you get your attention. All right, that's the propagation constant. That's equal to the square root of j omega epsilon times sigma plus j omega mu, pardon me, times sigma plus j omega epsilon, right? I'm just writing down what it is, and remember this gamma has to do with E naught e to the minus gamma z in the AX direction is the E field. So just to bring back where gamma is, right? It's the propagation constant. But if sigma is much greater than omega epsilon, then gamma is about what? Square root of j omega mu times sigma, isn't it? You see how the omega epsilon becomes inconsequential because it's small? Everybody? Can you all see that? Right. We're making this assumption. Sigma is much greater, 100, 1,000, a million times greater. So it's about this. This is sigma mu, or it's j omega mu sigma. Well, the square root of j, this is where I just want to make sure you understand that. J is really e to the j pi over 2 radians. Do you agree with that? Right? Isn't that another way to write j? E to the j pi over 2, or e to the j 90 degrees. Do y'all agree with that? So if I take the square root of j, really it's e to the j pi over 4, isn't it, class? Square root, just what? You take the exponential, divide by 2, correct, class? And nothing fancy about this. What is that? Well, that's cosine of pi over 4 radians plus j sine of pi over 4 radians, or 45 degrees. And what's the cosine of 45 degrees, anyway? 1 over square root of 2, isn't it? Right? What's the sine of 45? That's sine. Or I can write this as simply 1 plus j over the square root of 2. You all follow me? Nothing tricky. So when I come here, you see how I have the square root of j times the constants, right? I replace it with this, and I can say this is really 1 plus j, and then I'll take the square root inside here times the square root of omega mu sigma over 2. Now what I've done is I've taken the square root of 2 here, and I brought it inside, I brought it right there because this is really 1 plus j over square root of 2. If I replace j with that, the square root of 2 can be brought right inside it. Do you all agree with that? All right, keep watching. So this is equal to 1 plus j. Now what's omega in terms of f? 2 pi f, right? Isn't omega 2 pi f? So 2 pi f by 2 is just square root of pi f mu sigma. This is going to be real important. And here, remember, this is alpha plus j beta. So for a good conductor, we can say alpha in magnitude is equal to beta is equal to the square root of pi f mu sigma. This is real important. You all see that? Now, a good conductor means if you see alpha equal to beta, you got a good conductor. Or if you have a good conductor, you know alpha will be equal to beta. You with me on this? That's real important. If something else comes out of this, I'm not going to have time to really immerse myself in this, but it's the skin depth. Has anybody heard of skin depth in here? We're gonna do this next time. It's 1 over alpha, and it's 1 over square root of pi f mu sigma. That's the depth at which the electric field will decay to about 33% of its value. I'll spend more time in that next lecture. Y'all with me on this, class? Well, we're still not done. So first, we saw for a good conductor, this is the first point, this is true. That's the first. Now the second point is, what is the phase velocity? The fundamental definition of phase velocity. Anybody remember? It was omega over beta. Do y'all remember that? I'm not going to prove it right now, but it's true. So it was omega divided by beta. All right, now take a look. Well, omega is 2 pi f, right? Divided by beta is square root of pi f mu sigma. Now, do y'all see how we can simplify that down? Right? We got pi square root, what is this going to be? Well, we can see it's square root of f is up there, right? And then pi, right? And then 4, we can bring 2 inside, and it's divided by mu sigma. Now, it really doesn't matter how you write that, just so you appreciate it. I want to make sure you see one thing about this. What happens to the phase velocity as the frequency starts to go to 0? Take one look. Anyone? Well, what's the value of this when f is 0? It's obvious. 0, isn't it? 0, square root of 0 is still 0, right? That means the phase velocity could go to 0 in a good conductor. How can that be? Things are moving at the speed of light. Yeah, the photons are moving at the speed of light, but now they're ricocheting back and forth, and I don't want to go there. What I'm really saying is, in a good conductor, Tom Shumpert used to be a prof here, he used to say, I can outrun light in a good conductor. He can move faster. Look at sigma. If sigma is very large and the frequency very low, I can get something that's less than meters per second. I'm just telling you, you can. And that means, now that's not a wave moving along the surface of a wire in free space, that's into the wire, into copper. All right, it's moving in the direction. I'll spend more time on that next time. And everybody knows it's Friday, and we can get out of here. I didn't get to the intrinsic impedance, I'll put that up on OneNote. By the way, would you please make sure you can view the videos on OneNote? I'm going to give you homework. Do it for Monday, all right? And if there is any change in the policy of the class, I'll let you know. Please wear your mask and stay safe. If you have questions, see me up. Did you understand?